Okay, as I said, people did a good job. First thing they did was cleared fractions, which is correct. So we distributed a 4 all the way through. Okay, but don't forget when you're distributing, when you've got a 3-part and inequality like this, there's the left part, the middle part, and the right part, and you have to treat all 3 parts equally at the same time. So we're going to distribute the 4. When we distribute the 4 to the first fraction, remember how we do that. We always reduce first. 4 over 4 reduces to 1 times 1 is 1. We got to distribute the 4 to the 6. That's just regular distribution, so that's 24. And then again, 4 over 4 reduces to 1 times negative 3 is negative 3x, right? We got an x there. And then finally, don't forget to distribute that 4 all the way over to the 3, and we get 12. All right, so now we've eliminated the fractions. Everything looks a lot easier. The arithmetic will be easier. From this point forward, I'm just trying to isolate the x in the middle of that triple inequality. So you guys tell me, look at that middle expression, 24 minus 3x. That's got to end up just being an x. What are the 2 steps in order to isolate that x? What's the first thing we're going to do?
Minus 24.
Okay. Somebody different. What's the next thing? We subtract 24 first, and then what? Yeah. Divide by negative 3. Exactly. Good. Just using inverse operations, right? So we subtract 24 from all parts. And this is what I was seeing. So 1 minus 24, there's my negative 23. I have not multiplied or divided by a negative, so there's no reason to flip inequalities. I've got a negative 3x in the middle, negative 12. You already told me I'm just going to divide everything by negative 3. Which cancels those. And because I divided by a negative, what do I have to do? Got to flip the signs. This becomes negative over negative is positive 23 thirds. I've got my x in the middle. And here I've got a positive 4, but I can't leave it like that because it's backwards. With triple inequalities like that, with and inequalities, the inequalities have to open to the right. So I'm going from lesser to greater, just like a number line. So think how we do that. You can either just twist the entire thing around, or you can think of it like this. We can think of it as 2 individual inequalities. When we read a triple inequality, we always start in the middle with the x, right? We'd say x is greater than 4 and less than or equal to 23. So let's take that red part and let's just transfer it to the left side of the x instead of the right side. What does that say again?
X is greater than 4.
So I'm just going to say it going backwards. X is greater than 4. Okay. How about the blue inequality? Because there's 2 of them in one there. How do I read that one?
Less than or equal to 2.
Okay, everybody see that? Because I'm reading this one backwards. X is less than or equal to 23 thirds. We're just going to write it to the right instead of to the left now. X is less than or equal to 23 thirds. Like that. And we got it. Make sense? Okay, and I'm really just twisting the entire thing around. And then if I want to write this with interval notation, remember that the best way to do that is to graph it first and then use the graph to write interval notation. So my 2 numbers are 4 and 23 thirds, which is bigger than 4, isn't it? So it's to the right. And if I want to graph this, I want the values of x that are greater than 4 and less than 23 thirds. What would that graph look like? Okay, so I'm gonna start open endpoint at 4, and I'm going to graph to the right. I've got a closed endpoint at 23 thirds, and I'm graphing to the left. And I only want the parts that are in between, that are both greater than 4 and less than 23 thirds. So I'm really only graphing the parts in between the endpoints. That's the intersection. Everybody see that? Okay. And that's how and inequalities normally look, isn't it? They look like one segment, including all the values greater than some bottom limit and less than some top limit, right? Okay, phones should all be up here if they're not up here, please put your phones up here. So does that make sense? That would be the normal look for an and inequality. Back to business here. So today we warmed up. Now today we're going to look at solving two things. Really minor steps forward compared to what we've already done. Nothing really new. We want to look at some tricky compound inequalities that don't end up looking like we would expect them to look. Normally we know that if we're solving an and inequality, compound and inequality, it looks kind of like this, right? I get a single segment with a lower endpoint and an upper endpoint. If I'm solving an or inequality, remember that usually looks like one interval going to the left to negative infinity and one interval going to the right to positive infinity. It's like I'm rowing a boat towards you, right? Those are the oars sticking out of the boat. Those are the normal looks. Sometimes when we do compound inequalities, they don't look the way we expect them to. We want to look at some of those today. And then we want to look at how we can deal with unions and intersections of sets, which is really much easier than compound inequalities, you'll see. So let's look at this as an example. Is this an and or an or inequality? It's and, right? That's the and symbol, isn't it? So it's an and statement. So then how many, when we come up with our solution, the solution of an and inequality is the part where how many of those inequalities are going to have to be true at the same time? Both of them do, right? If I ask you to raise your hand if you have a dog and you have a cat, you have to have both of those in order to raise your hand. All parts of an and statement have to be true to be a part of the solution to the statement, right? Okay, so let's do these one at a time. What are the two steps? These are pretty simple. What are the two steps to isolate x in my first inequality? Subtract 5. Let's get different contributors here, so be brave. Subtract 5, what else? Somebody else hasn't contributed. What's the next step? Divide by 2, there you go. So we subtract 5, we get 2x is greater than 14. We divide by 2 and we get what? X is greater than what? 7, there we go. Okay, so there's part of it. And how about the other one? What are the two steps in order here? New people, be brave. First thing we're going to do. Add 6 and then divide by 4. There you go. So 4x is greater than 24. If I add 6 to both sides, I divide by 4. Don't I just get x is greater than 6? Okay, that's a little different for an and statement. Usually the and statements that we've seen have had, well, we've been in situations where x is greater than one number and less than a different number. Okay, that's the normal kind of what we'd expect to see from an and statement. That's not what we got here. We got x is greater than one number and x is greater than a different number. So how do we resolve that? Well, the best way to resolve these kinds of situations and come up with a solution is to graph it. And from the graph, we can see what's going on. So if we graph this statement, we have numbers at 6 and 7. What does the blue graph look like? X is greater than 7. Okay, I'm going to the right. Starting where?
7.
With what kind of endpoint? Open endpoint. Okay, good. So it just looks like that, doesn't it? How about the red solution? What would that graph look like? X is greater than 6. Okay, open endpoint to the right. And you already told me that an and statement is an intersection. It's where both have to be true at the same time. So based on the graphs of each of those two inequalities, what is the solution to the and statement? Where are they both true at the same time? After 7, yeah. That's where they overlap or intersect, isn't it? Okay, so this is the solution right there. That's the solution. X is greater than 7. Okay? Make sense? What if this had been an or statement instead? What would the solution have been? 6 or greater than 6, right? Because for an or statement, we want every place that is either red or blue or both, right? Any place where one of those is going on is a part of the solution. That's a union instead. Okay? How about this one? Same kind of thing. So 2 steps in order to solve the first one.
Minus 6
Okay, so I subtract 6, I get 4x is less than or equal to, what, 28 if I subtract x from 6, or 6 from both sides? Now what? Divide by 4, what do I get, everybody? X is less than or equal to 7. And or? Or. It's an or statement, isn't it? Okay, or. How about the next one? Add 6, so 3x is greater than or equal to 12. And what do I get? X is greater than or equal to 4. Okay? Again, we want to see what this looks like. So we graph it. Got numbers at 4 and 7. So if I graph the blue one, x is less than or equal to 7, doesn't that start with a closed end point at 7 and I graph to the left? Okay? Red one, x is greater than or equal to 4. Closed end point at 4, graphing to the right. Now this is an or statement. So I want every place where at least one of those is true. Right? Where could an ant stand on the number line and be either in a blue or a red region? Everywhere, right? Everywhere. And is it confusing? What about the middle? Do you think because it's both that wouldn't be included? No, it doesn't matter. If it's red and blue, then certainly it's red or blue, right? Red and blue just means you get both. You only need one, but you actually get both. So the or statement is going to be true every place that is blue or red or both, because both is that counts. Okay? So that's everywhere, right? So my answer is all reals. How would I write that using interval notation? What's the left end point of that purple interval? Yeah, negative infinity on the left, positive infinity on the right, and we got it. Make sense? Okay, try one of those. Go to the boards and try that one. Yeah, I want the graph, and then I want the solution, the simplified solution. All right, so I saw good stuff. We have two separate inequalities. You're going to solve them individually. So people did a good job of seeing that they needed to distribute 4 to the first inequality. And if we distribute that, we're going to get 16. 4 over 4 is 1 times 5. So we get minus 5x is less than 36. Right? Yep.
There's two fractions in the one side, and there's like two different denominators. Which one do you choose?
Okay, you have to do them separately. So now, so that we have and. So here's the and statement. And now we're going to do this one over here separately. Oh, what were you saying?
Like if there was another one next to 5/4.
Oh, I see. Like if there were 4/3 or something? Oh, I got you. Okay, yeah. Okay, good question. So what if, like if this were 4/3 and that were 5/4, then we'd have to find the smallest number that 3 and 4 divide into, which would have been 12. Okay, and remember what our process for that is. You take the biggest denominator and you look at multiples of that until you find the first one that's divisible by the other denominator, which in this case would have been 3, and so would have been 12. Okay, make sense? Okay, good question. All right, so then on this guy, we were going to distribute a 6, right, to undo that 6. So 6 over 6 is 1 times 1 is 1. 1x we just would call x. 6 times negative 4 is minus 24. And then 6 times negative 5 is negative 30. So there we get our two inequalities fraction-free, which makes it a lot easier. 2 steps in order to isolate x in the first one. Subtract 16 and then divide by what, everybody? Negative 5. There you go. So subtract 16. This is the stuff I was seeing. So we get negative 5x is less than 20. We divide each side by negative 5, which gives us x. I divided by a negative, so what do I have to do? Got to flip it. X is greater than negative 4. And What about over here? So we're just going to add 24, and that's it, right? In our second one, we get x is less than or equal to -6. It's an and statement, so we always want to try to write and statements as one big statement if we can. To do that, we're going to graph it. Graphing it is always going to make finding the solution easier with these compound inequalities. So we've got numbers at -6 on the left, -4 on the right. X is greater than -4. Doesn't that just look like that? X is less than or equal to -6. Doesn't that just look like that?
So it's no solution.
Yeah, so it's no solution because an and inequality is looking for the intersection or the overlap of the two parts, right? These never overlap. So the answer is no solution. In inequality notation, all we could do is just that, or an interval notation. Okay, make sense? All right. Okay, I'm going to skip that one for now. And last thing I want to show you today, really simple. It's just we're going to look at, instead of looking at and or statements, we're going to look at just the union or the intersection of sets, which is very similar to what we've been doing. U is the way we say or for interval notation. So a union of sets is going to be very much like an or inequality, same idea. And an and, where we're finding an intersection, an intersection, is going to be similar to an and compound inequality. Okay, so let's think about this then. First example in the blue box. They give us 4 sets, and they want us to find, how would we read this? This is the intersection of sets B and C. That's how we'd read that. It's the intersection symbol. So intersection means we want to find all the parts of the sets that are in both at the same time. That's the intersection. Okay, well, what is that going to be? The set B, the set of all x such that x is an odd integer. So that's just a fancy way of saying all odd integers, right? Set C only has 4 elements, 2, 3, 4, and 5. So what's going to be the intersection of the set of all odd integers and the set 2, 3, 4, and 5? 3 and 5. Everybody see that? Because those are the only 2 parts that appear in both sets that overlap. Give me thumbs on that. Does that make sense? Okay, so that's it. That's all it would be is 3 and 5. Okay, how about this next example? A is the set of all odd integers. B is the set of all even integers. So what's the union of those 2 sets going to be? Union is just the sum, right? It's going to be if we combine all the parts of all the sets, what would we get?
All integers.
Yeah, right? If I take all the odd integers plus all the even integers, that's all integers, right? That's every integer is either odd or even. So that would just look like every integer, both odd and even. Okay, now think about the next one. What would the intersection of those 2 sets? What's that going to be? What's the intersection of the set of odd integers and the set of even integers? Nothing, right? There are no parts that are in both. So the intersection would just be the empty set, right? Make sense? Okay, we're going to be almost out of time. Go try one of these. See if we can crank this out real quick. So there's set A. It's got 4 elements, and set B has 5 elements. That's it. None of them are infinite. Go write down what's the union of those 2 sets and what's the intersection of those 2 sets. So this one was an example of one of those yesterday that's a little bit tricky, right? You want to use the graph to write your final solution. People did the math correctly. They did the algebra correctly as far as I saw. So that when we solve for x in this first one, people, what they do, they added x to both sides typically, which is a good idea. Canceled those guys. We subtracted 10. Pushed the variables to the left, and that gave us negative 9 and 3x. So we divided by 3, and we got x is greater than negative 3. Maybe we want to flip that around and write it this way. So there's one part of our solution. Or, how about the other side? On the other side, we subtracted x and subtracted 3, and we got 3x is greater than negative 3, so x is greater than negative 1. Isn't that right? Those are the two you got? Okay, it's an or statement though. So it's an intersection or a union. A union. Think what a union means now. A union means that the graph that we're going to keep is going to be every place that is either blue or red when I graph those things. Every place, all the x values on the number line that make either one of these true would be part of our solution because it's a union. It's all encompassing, right? Intersection would be more exclusive. That's only where the two graphs intersect. So let's graph this thing and see what happens. Our numbers, our important numbers are negative 3 and negative 1, right? And you guys all would tell me that the graph of x is greater than negative 3 looks like that, and the graph of x is greater than negative 1 looks like that. Okay, we don't want to leave the answer like this though because it's too complicated. We can make it much simpler. Where are all the places? We're going to graph in purple our solution. What are all the x values then that are either greater than negative 3 or greater than negative 1? What would I graph? Yeah, negative 1 to the right, right? I want it, my solution is going to be every place where an ant could walk on the number line and either be on the blue solution or the red solution. And so that means that, doesn't it? Everybody see that? So the solution, we have to write it this way too. This would be wrong to write it like this. This would be unsimplified. What we end up getting is x is greater than negative 3 is our solution. Okay, give me thumbs on that. You see why? Everybody see why that's true? Because that's every place, that's the union of the two inequalities. Okay? If I wanted to, and here's the graph, right? And so in interval notation, it would just look like that. Okay? Those are tricky. Those are tricky because, I mean, they're not the normal kind, right? Normally, we'd expect to have x being greater than some value, some big value, and less than some negative value, and so we get ors on a both. That's kind of what we'd normally expect, but it doesn't always work that way. All right, so for today,